creating these orbitals that have nodes associated with them. And so that's what we're going to talk about now. And what a node is it is a location, according to the Schrodinger equation, where an electron will not exist. A node is a location, according to the Schrodinger equation, where an electron will not exist. So, when we look at the result of a Schrodinger equation, when we look at a 1s orbital, there is no node. But when we look at a 2s orbital, there is a spot on the x-axis where there is no electron density. When we look at the 3s, which is probably the most obvious from this distance, there are two spots where there is no electron density, meaning that the curve resides on the x-axis. What this electron density diagram looks like. For a 1s, again, it looks like a sphere around the nucleus. And for the most part, and there is no node associated with that. But when we get to a 2s, you have the centerpiece, which is the 1s, and then you have the blue, which is representing the 2s, and in between that yellow 1s and the blue 2s, you will notice that there is this white region. That white region represents a node where there is no electron density. That means that there is no electron that exists there. When we get to the 3s, you have the 1s orange dots in the center. You have the 2s blue dots surrounding it, and you have the 3s orange dots surrounding that. And what you will see is there are two white lines that represent nodes. Again, that is where an electron does not exist according to the electron density map that is generated from the Schrodinger equation. Now, this is just simply another way to look at that. And again, there's going to be gaps in between the 1s and the 2s. And there's going to be a gap between the 1s, the 2s, and then the 3s. And it's just another way to look at it. Questions? Yes.
Wouldn't the nucleus be a node? Because you never find the electron there.
The nucleus technically is a node. But when we're looking at these electron density maps, you're considering the y-axis to be the nucleus. Now, here is a diagram of a 3p. How do I know it's the 3p? Well, first thing I know is that it is a p. And the reason I know it's a p is because this looks like a dumbbell around, with the nucleus being right here in the middle. Kind of looks like a dumbbell. Now, if I think about the p, p means L is equal to 1. We do not have an angular momentum quantum number of 1 until we get to shell 2. We do not have an angular momentum quantum number of 1 until we get to the principal quantum number of 2. Because of the mathematical definition. What that means is that this inner piece has to be the 2p. Again, we do not have an L of 1, which is what a p is, until we get to the second shell. So this inner one has to be a 2p, and then further out is the 3p. So that is how I knew it was a 3p. I started with the fact that it had to be a p because it was dumbbell shaped. The next thing I did is determine where the p's begin, which is in the second shell. And then that meant that the inner shell had to be 2. The next one out would be 3. So this is a 3p. Now, when you get into P subshell and D subshell, you actually have 2 types of nodes. You have an angular node and you have a radial node. The angular node exists on the XYZ axis and is associated with the nucleus. The radial node, when we think of radial, we think of radius, meaning we think of a circle. This has 1 radial node because this has 1 circular node, again, where the electron does not exist. Now, how do you predict how many nodes everything has and what type of nodes it has? Step 1. You're going to identify the orbital you're evaluating. You heard me. When I looked at the P, I was like, oh, that's a dumbbell shape. It has to be a P. In the previous slide, I said it's a sphere. It has to be an S. So you're going to identify the type of orbital you're dealing with based off of its shape. Is it an S, meaning sphere? Is it a P, meaning dumbbell? Is it a D, meaning most of them are a cloverleaf? What is it? From that, you're going to count from the subshell closest to the nucleus outward. But to do that, you have to understand where that particular orbital, that particular type of orbital starts. An S starts in the first shell. A P does not start until the second shell. A D does not start until the third shell. And an F does not start until the fourth shell. From that, we can determine the total nodes. The total nodes will be in, what shell is it, -1. That will equal your total nodes. N -1 equals the total nodes.
Would you increase the different types of nodes as you went up because the dimensions of the orbitals change? So when you went from S to P, you gained one, and then when you go to like D to F, would you gain another type?
Okay, So when you go. Repeat, please.
So in S, you only have one type of node. But when you go up to P and D, you have another type. If you were to go to F and then your theoretical G, would you have?
No, you're still only gonna have radial nodes and, angular nodes. It's just the quantity of those vary. Okay. So once you figure out the total nodes, how do you know how many radial nodes and angular nodes you have? You can determine the angular nodes because the angular nodes will equal whatever L is. So again, if it's an S subshell, L is 0. If it's a P subshell, L is 1. If it's a D subshell, L is 2. If it's an F subshell, L is 3. And technically, the equation for the radial nodes is it's going to be n minus 1 minus L, or in other words, it's the total nodes minus the angular nodes. That's the easiest way to get that. The total nodes minus the angular nodes will be the radial nodes. We're going to see this in action. I'm going to do a couple of examples. Okay. So let's talk about the 2s orbital and let's see how you use those equations that I gave you. Step number 1. I know that this was an S subshell because it's spherical. Step number 2 was to figure out exactly which S it was. Well, S begins in n equals 1. So this pink dot represented the 1s, and the next one out represents the 2s. So I am looking at a 2s subshell. Where the 2 tells me the n value and the s tells me the L value, specifically that L is equal to 0. Now your total nodes
was equal to n minus 1. So we're talking about 2 minus 1, or in other words, 1. There is one node. Your angular nodes equals L. Well, L is equal to 0, therefore your angular nodes is 0. So therefore, your radial nodes, your radial is technically equal to n minus 1 minus L. Or in other words, it is 2 minus 1 minus 0. So it is equal to 1. That radial node is this white region between the pink and the blue subshell. And it is a radial node because it forms a radius. I would do something similar for the next one. Again, I see it as a sphere. So it's an S subshell. I know S begins at 1. So that means that this is a 1S, the blue is a 2S, and the next one out is a 3S. So this is a 3S, that's horrible, 3S orbital. And I would have done the math the exact same way. And what I would have found out is that there are 2 nodes, both of which are radial nodes. Let's look at another example. Let's look at this. Let's first look at this one over here. First of all, what is it? Is it an S? Is it a P? Is it a D? Is it an F? It's a P subshell because it is dumbbell. What N value do P's begin in? 2. So the N value is equal to 2 for the start of the P's. Now it's really hard to see, but there is one right here that's little that represents the 2P. The next one out would be the 3P. So we are looking at a 3P subshell where the 3 represents our N value and the P represents the L value, which L is equal to 1 if it is a P. Now, for your total nodes, it is equal to n minus 1, so it is equal to 3 minus 1, or in other words, we have 2 nodes. For your angular nodes, that is equal to L. Well, L is equal to 1, and therefore there is one angular node. That angular node splits the two lobes of the p orbital. Then your radial is total minus angular, or in other words, it's 2 minus 1, so therefore there is one radial node. And the radial node, you can't see the other p, but it would basically be between the 2p and the 3p. You don't have to be able to draw the angular and radial nodes. I'm just trying to illustrate where they are so you can see radial means a circle. Angular means on the XYZ axis. Okay, what type of subshell is our next subshell? It's a D because it is a clover leaf. D starts when n is equal to 3. Therefore, the smallest of these will be the 3D. The next one will be the 4D. And the one we're actually evaluating is the 5D. So we are looking at a 5D. The 5 tells us the N value, the D tells us the L value, which is L is equal to 2. So our total nodes is equal to N minus 1. So that is going to be 5 minus 1, or in other words, there are 4 nodes. Our angular nodes are going to equal L. Well, L was equal to 2, so therefore there are 2 angular nodes. Those angular nodes are on the axes between the 4 leaves of the clover. Then the radial nodes, radial is going to be the total minus the angular, or in other words, 4 minus 2. So there are 2 radial nodes. The radial nodes, being a circle, will separate the D subshells. Questions? Again, you don't have to be able to draw where the radial nodes are or the angular nodes. I'm trying to illustrate them so that you see why there are the numbers they are, but you just have to be able to tell me how many of each there are. Questions? I did remove the nodes off of the last homework, even though it apparently didn't save yesterday. I got it to save today. So those will come back tonight for next week. Okay. We will come back to using quantum numbers because your quantum numbers are embedded into that periodic table. Right now, we're just going to discuss some of the arrangement of the periodic table. The periodic table is probably one of the most predictive tools there are out there. I can figure out, without knowing what element 115's properties are likely to be. The reason is because it's directly under bismuth, which is directly under antimony, which is directly under arsenic, which is directly under phosphorus, and I understand phosphorus and nitrogen. I don't even know bismuth, but I know how nitrogen and phosphorus behave. So that gives me a pretty good idea. Some of the periodic properties are density. The further you go down on the periodic table, the greater the density. Atomic size. Let's see how this works. Because I'm going to be over here quite a bit, but I don't want to run back and forth. Francium is the largest atom on the entire periodic table. Helium is the absolute smallest element on the entire periodic table. In fact, as we will discuss later, the atomic size increases as you go down a group due to shielding, and the atomic size decreases as you go across a period due to the Z effective. Ionization energy. Francium has the lowest ionization energy of all elements. Electron affinity. The elements that give off the most energy when they absorb an electron is going to be fluorine. Well, actually, it's chlorine. Fluorine's a close second. So basically, we can predict a lot of information simply by knowing where something is on the periodic table. And as we're going to see, it is directly related to the electron configuration, which is directly related to quantum numbers. So quantum mechanical theory is what explains the electronic structure of an atom. These quantum mechanics is what explains the structure of the atom. As we're going to discuss in this chapter, that quantum mechanical theory allows us to build the electron configurations. The electron configuration being the address of every single electron in an atom. And it is due to that quantum mechanical theory that we can obtain the properties of those atoms simply by looking at the periodic table. So let's just look at some of this information that's embedded in the periodic table and how it is related, or how you can use the periodic table to predict it. Well, first of all, these elements are arranged in order. Well, originally, Mendeleev arranged the atoms of the elements in order of increasing mass. And for the most part, if you look at these masses, that does work. But every once in a while, you will come up with something that does not work, like tellurium and iodine. They're slightly, the masses are not in order. So instead of arranging the periodic table according to mass, they decided to arrange the periodic table according to atomic number, which is what we've already discussed. The atomic number telling us how many protons are in the nucleus. When they arranged the periodic table by atomic number, they noticed in these smaller elements that every 8th element behaved like the one above it. So lithium and sodium behaved similarly. And helium and neon and argon behaved similarly. Fluorine and chlorine behaved similarly. So they noticed when they took the elements and put them in atomic number order and then arranged it by every 8th element, they saw periodic trends. Now, these periodic trends are extremely important. First of all, we can describe things by its group number. Lithium, sodium, potassium, rubidium, cesium, and francium. They all behave similarly. They are a family called the alkali metals. Another word for the family is a group. Beryllium, magnesium, calcium, strontium, barium, and radium all behave similarly. They're a family called the alkaline earth metals. But most of the time, I will refer to them as group 2. When you get over to the right-hand side of the periodic table, fluorine, chlorine, bromine, iodine, astatine, all behave and tennessium, all behave similarly. They're a family called the halogens. Or as I will refer to them a lot, as group 17. And then you have group 18. Group 18 are known as the noble gases. They are a group of fairly unreactive elements. So the group is important. And as we're going to find out, when we look at these families, their electronic structure is going to always have something in common. The other thing that is on the periodic table are periods. Again, every eighth element, we started a new period. The periods increase 1, 2, 3, and so on. The period, as we're going to find out, is extremely important with respect to the atomic size. We're going to find out that when you get down to francium, for example, its outermost electron is in the 7th shell away from the nucleus, in the 7th principal quantum number away from the nucleus. So these period numbers are actually going to have a relationship with the quantum number, the principal quantum number. I already went over named groups. You've got your alkaline metals, your alkaline earth metals, your halogens, and your noble gases. Those are going to be the named groups that we will focus on. The rest of them will typically just call them by their, that was weird. We'll just call them by their group number. Now, I do want to mention the group numbers a little bit more. So the group numbers on this periodic table list 1 through 18. You will see another variation where this will be 1A, 2A, bump over to boron, and that's in 3A, 4A, 5A, 6A, 7A, 8A. And then the transition metals are Bs, and they start at 3B and go through 12B. That is an older naming system, the A's and the B's. A lot of people like to use the just numerical group numbers, but depending upon what periodic table you look at, you may find either one. Okay. So the periodic table, we've already talked about groups and periods. Now let's talk about main group elements, transition metals, and intertransition metals. Group 1, 2, 13 through 18 are known as your main group elements. In other words, they're the elements that stand the tallest on the periodic table. They're the groups that stand the tallest on the periodic table are your main group. Now, group 1 and group 2, their outermost electron will be in L of 0, meaning they're going to have their outermost electron is in the S subshell. Group 13 through 18, their outermost electron are going to be in L is equal to 1, meaning their outermost electron is going to be in a P subshell. Group 3 through 12 are known as your transition metals. Your transition metals, the outermost electron are going to be in L equals 2, or in other words, D subshells. And then these two rows at the bottom of the periodic table, they technically belong, but you'll notice the number 57 drops down to 58. This row, this top row, are known as the lanthanides because they follow lanthanum. The next row you'll notice starts at here is 89, and then we drop to 90, and we go across. These are known as the actinides because technically they follow actinium. Now, these are called intertransition metals because if you were to actually draw the periodic table according to atomic number, these two rows would be placed right here, and this table would wind up expanded way over there. They do this to condense the periodic table so that it'll wind up on you can put it on a sheet of paper easily. That's the main reason they do it. Now, the lanthanides and actinides, which are your intertransition metals, their outermost electron will wind up in L is equal to 3, meaning that it will be in an F subshell. You're quickly seeing, hopefully you're quickly starting to see. The group numbers related to N, where it's located on the periodic table, is related to L. The periodic table has been arranged according to, or has basically its properties, these elemental properties, is all based off of quantum mechanics. Now, another division is the periodic table can be arranged according to metals, nonmetals, and metalloids, which I've actually already introduced to some degree. The metalloids. If you draw a line from boron to astatine and add germanium and antimony, draw a line between boron and astatine and add germanium and antimony, those are going to be your metalloids. The metalloids separate the metal from the nonmetals. Now, why is it important to know this division of metals and nonmetals? Multiple reasons. Number one, we can predict properties. Your metals tend to have high melting points. They have high boiling points. They are malleable, meaning they can be banged out into sheets of metal. And they're ductile, meaning that they can conduct electricity. So again, if it's on the left-hand side of your metalloids, which is boron, silicon, arsenic, tellurium, astatine, germanium, and antimony, it's on the left-hand side of those, it's going to have those types of properties. Whereas if it's on the right-hand side, they don't tend to conduct electricity very well. They can't, most of them aren't even solids. They're gases and liquids. So they're not malleable. They're not ductile. They tend to have low melting points and low boiling points. Now, that is a broad statement because there are exceptions to everything I've just said about the metals and the non-metals. But in general, you can predict the properties with what I've just said. Now your metalloids, they're somewhere in the middle. They're called metalloids or semiconductors because they can conduct electricity, but they're not going to conduct electricity as well as the metals. Again, folks, whoops. This periodic table if you arrange it according to atomic number, it has predictive power. It has predictive power because of similar electronic structures are found within a group. Those similar electronic structures, those electron structures are related to quantum numbers. Now, one thing I haven't mentioned is a little bit more about the periodic table. When we're talking about the S's or the P's, you can look at the group number to figure out what, excuse me, you can look at the period number to figure out what N is. Now, with the D's, your transition metal, if I am looking at scandium through zinc, the N value is going to wind up as the period number -1. Again, for your transition metals, the N value, the principal quantum number, is going to wind up as the period number -1. Your inner transition metals are going to wind up as the period number that they should be in. So this should be in period 6 -2 to figure out the N value. Now, you may go, why? Why is it N-1 for transition and N-2 for inner transition, where N is equal to where the period number in relationship to the period number to get to N? Why? The answer comes into how an electron fills into the energy levels. But we're not there yet. What I do want you to know is that when you're in the first shell, the only orbital that is available is an S. When you're in the second shell, you have S and P available. That doesn't mean they fill. That means they're available.
when you're in the third shell, you have S, P, and D available. That doesn't mean it fills automatically. In the in the fourth shell, you have S, P, D, and F available. So that notation where S and P is equal to the period number for N. For the transition metals, the N value is the period number -1. And for the intertransition metals, the N value is the period number -2. Is because these orbitals exist, they just don't fill in that exact order. We don't fill them in this exact order that's listed. Instead, the periodic table has been arranged according to the energy. Yes.
Gave us, like, the, like, 57 and 89 are included in the bottom ones, but they're not for like the round separation.
It really is dependent on, some periodic tables include 57 and 89 in the intertransition metals. Some include them in the transition metals. I have no explanation for why different periodic tables behave differently. Okay, so again, this periodic table has been arranged for you according to energy. The first one, though it's very difficult to see, is the 1s. Hydrogen and helium are the 1s. The next thing that is listed is the 2s. Lithium and beryllium are the 2s. The next thing that is listed in energy is the 2p. Boron through neon are 2p. The next thing that is listed is the 3s. Sodium and magnesium are the 3s. The next thing that is listed is the 3p. Aluminum through argon is the 3p's. The next thing in energy is the 4s. That is why potassium and calcium are listed on the periodic table in this particular order. After that, we get to the 3Ds, and that is where you get scandium through zinc. After the 3Ds come the 4Ps. And that is why you have gallium through krypton. That's why 4P is listed after the 3D, is because it's all related to energy. If I keep going, I would have the 5S, then the 4D, then the 5P, 6S. At this point, everything gets very, very close together. Technically, the next thing in line, energy-wise, is the 4Fs. And then the 5D, 6P, 7S, 5F, 6D, and then 7P. So again, the easiest way to remember this is to start with the period number. For your S, for N is equal to the period number for your S's, and N is equal to the period number for your P's. N is equal to the period number minus 1 for your D's, and for your F's, it's N is equal to the period number minus 2. But the reason it is arranged the way it is not only atomic number, but also related to energy. Questions? And the reason the periodic table got arranged in the first place, it started with atomic number. Then then elements that behave similarly got put into the same group or families. And then once we were able to actually understand the electronic structure, we realized that all these properties and all of this information, it all comes back down to that quantum mechanical model and the energy levels. Now, again, I said the 3D, the 4S wound up filled before the 3D. Everything, folks, is all about what the Schrodinger equation gives us. If I look at the 4S, which is the solid line, compared to the 3D, which is the dotted line, you will notice that this little amount of the 4S got filled before the 3D. That's why it got listed before the 3D, is because it's just a fraction lower in energy. I've already done that. We're not going to get far into this because I'm getting close to running out of time, but I'm going to at least introduce the process. Of developing electron configurations. And the electron configuration tells you where every single electron in the atom exists. It always fills from the shell closest to the nucleus outward. It always fills so that the electron is in the lowest energy level possible. Because, folks, energy is the real story behind everything. Energy is the real story behind everything. So electron configurations show the particular orbitals that electrons occupy for an atom. And the ground state electron configuration, the electrons always fill the lowest energy state first. I am specifying find the ground state because an excited state would have an electron in a unexpected location. Example, when we were working with hydrogen, we took the electron that was in the 1s and we exposed it to electricity and we shot it up to the 6. That would be putting it in the excited state because it's in a place where we didn't expect to find it. But the ground state puts the electrons in the lowest energy levels first. So, with hydrogen. Hydrogen is atomic number 1. Which means that it has 1 proton and 1 electron in the neutral atom. That 1 electron is going to enter into the lowest energy level, spin up. Now, what that means is our N value is 1. Our L value is based off of the letter. So an S means that L is equal to 0. The M sub L, if you'll recall, M sub L can be anything from a negative L to a plus L. So if L is 0, that means it can be anything from a negative 0 to a plus 0, meaning our option is 0. And because we put it in spin up, it's a plus 1/2. Let's look at another element. Let's look at helium. Helium is atomic number 2. So it has 2 protons and 2 electrons. The electrons will go in the lowest shell, lowest subshell. The first one goes in spin up in the 1s. The second one goes in spin down in the 1s. Because each orbital, each of these little lines represents a orbital. And each orbital can take 2 electrons. So each line can hold 2 electrons. So we would typically write this as 1s superscript 2. Now, again, the number tells us what N is. The letter tells us that since it's an S, that L has to be equal to 0. So when I'm writing N, L, M sub L, M sub S, my first electron is 1, 0. Again, the only M sub L allowed in a 0 is 0. and the first electron is spin up. So it was a plus 1/2. The second electron was 1, 0. Again, M sub L has to be 0 because that's the only value that's allowed for an L of 0. But the second electron is a negative 1/2 because it was spin down. And those are the two quantum numbers for the helium. We're going to spend a lot more time on this on Thursday because electron configurations tell us the story. And so don't forget, if you left your umbrella or you left a calculator, or if you haven't picked up the sheet for the 11 o'clock or the 2 o'clock labs, come grab them. And the other thing I want to say, is that 2 weeks from today is your next exam. I went ahead today and put together next week's folder, which lists out what I expect to be on the next exam. Some of which you're ready to do, some of which you're not ready to do. But anyhow, I wanted to let you know it's coming so that you can start preparing as you need to prepare. Now, with that, I'll see you on Thursday.